course to draw attention to my presentation, so I definitely chose one in that case called Beyond the Relational Database. So I guess that's not working, so I'll just... So in the beginning, is that working? There was something that you guys probably are familiar with, Oracle, right? In 1979, Oracle became the first production relational database out there, right? So that's some 33 years ago, a couple years younger than myself. Sorry, no age discrimination intended. And, most of the things were good back then, right? So 33 years ago, we had technology invented, and for the past, we've rolled on with it. And over time, things have kind of changed, right? I mean, I think anyone can agree that the technology that exists today and how we interact with it is not what it was or what it used to be. And kind of what happened at the beginning of all this is humans were the source of data, right? Most applications were run local within a company or a network, and they use something like this to enter data into their systems. You may be familiar with it, I'm not sure. It's a keyboard. So only so much data could be created so fast, right? But now there are a lot more sophisticated networks out there. We have this thing called the internet. Maybe you've heard of it. It's kind of a big thing, I guess. And now, instead of a small group of people in a company having one of these things, everyone in the world kind of pretty much has one, right? A lot of people on the internet these days, but not only just a keyboard, but any device, right? Mobile, etc. You don't just need a keyboard anymore. So kind of what happened was things changed, right? And we ended up with also machines, right? So not only is input being captured from keyboards and humans, but machines are emitting data, right? So think about your mobile phone, like all the different things that get emitted from your phone. Sure, you send texts or email, but what about GPS locations and applications that track that? And what about sensor data and metadata being tracked on how fast transactions are taking somewhere? So the data that has been created just kind of has exploded recently. And there's kind of this new term that's out there that you may have heard of or may have not, called big data, right? So big data is kind of a lot of the buzz. And while I won't spend much time going into exactly a definition of big data or what big data is, just show of hands, how many people have not heard of big data? Anyone? Oh yeah, there's always one slow kid. But I'm glad to hear that glad to see that the rest of you have heard of it. So just kind of put this in perspective. Here's a little graph that I kind of found, and I thought it was kind of interesting, and definitely can file this under up and to the right, as a company basically was tracking the number of times big data was mentioned and how frequently that has happened over the past 3 years. And there seems to kind of be a logarithmic shape to this curve on the right-hand side. So I would think that it might be something important to consider or take under consideration. James? Oh, the question is, did they use big data to find this? And I have a suspicion that the answer is yes. So it's a dog food problem, right? Yeah. So kind of what I'm here to talk to you about is something else that you may or may not have heard of, but it's Hadoop, right? So how many people here have not heard of Hadoop? Anybody? Okay, one or two. Okay, so Hadoop is kind of a relatively newer technology or an emerging technology, and is basically based off a Google paper about how to program for distributed systems. And Yahoo has implemented, or it started as a Yahoo project, and now is a generally open source project supported by much of the community. And a lot of big data problems are being solved by the Hadoop ecosystem. So that's kind of a little bit about what Hadoop is. And kind of to put it in a single statement, if you will, is Hadoop is a distributed storage and processing platform, right? So it kind of has two major components. So there's a storage component to it, meaning more or less a file system. And there's also a processing component to it. So there's a layer that you can apply processing to on top of the data, right? So you may have heard a statement similar to this at Oracle World or in relation to Exadata, and that is moving processing closer to the data, right? So someone must have written a law or made a comment that as data approaches infinity, it's easier to move logic to the data than to move the data to the logic, right? So we want to optimize to move the more portable thing, and code is generally more portable than data, right? So especially as data gets very large. So just to mention some of the things in the Hadoop ecosystem. So at the base level, we have the Hadoop Distributed File System, or HDFS. And HDFS is a kind of user-land file system that runs on a bunch of commodity-based computers, and it basically scales to very large clusters. By very large, I mean thousands of nodes, right? So that's probably a bit bigger than any storage solution that a commercial vendor can really offer today, right? I mean, it's quite large in comparison to most things that exist. And what's kind of cool is on top of that is the programmatic layer, right? So I said Hadoop also includes a processing layer. So that processing layer has a bunch of components built on top of it that allow it to interact with the data that's stored in HDFS. Some of those are Flume, HBase, Hive, Pig, etc. I won't go into details of all these names. Some of them are high-level languages for MapReduce itself. Some of them are key value stores. Some of them are machine learning algorithms. So the kind of point here is that this is the application layer level, right? So people can build things and deploy them on a distributed cluster to allow massively parallel operations on very large data sets to take place. Now, above and beyond that, there's kind of like some names here that probably most of you are familiar with. Informatica, MicroStrategy, et cetera, right? These are tools from mainstream vendors that I'm sure one or more of you have in your shops, right? So what's happening in this ecosystem is that vendors are now deploying solutions and providing solutions to interact with the application level stack to provide you with very large and scalable solutions on very large data sets. So in a nutshell, the platform is not just storage and not just processing, but also, there's application levels going on top, or application is coming on top of that. And as the platform gets more mature and vendors get deeper solutions, there will be more full stack solutions that become available, much like, back in the early relational database times where, most of the programs were written by engineers, software engineers, and then eventually those programs kind of got grouped into products that vendors started selling, right? And that's a lot of what the ecosystem in the database land is today. So there's so much to cover. I'm just going to kind of pick a few things to focus on. And there are three things I kind of wanted to talk to you about today. And that is MapReduce, Hive, and Pig. So just a little bit on what MapReduce is. So MapReduce is an extraction layer that allows engineers to basically perform simple computations, and it hides a lot of the details of parallelization, data distribution, load balancing, etc., and also gives you fault tolerance. So the platform itself is designed in mind to expose a easily used API that helps you accomplish all of these things without having to worry about an engineer for fault tolerance or for load balancing. The platform underneath it takes care of that for you. So you can write very simple programs, deploy them to massive clusters, and let the platform itself kind of manage the hard and heavy lifting parts. So how many people here have heard of MapReduce? Right, quite a few. So just kind of a little primer in MapReduce. And here's kind of a pseudocode example. And one of the examples that is frequently used is word count. So word count we basically take a file and we try to find out how many times each word in that file occurs. And the map side of that problem basically is to read in the document and split it into words, that word with the number 1. So every word we find, we split it off and project it as a word and a 1. And I have a picture in the next slide that kind of explains this. And once we kind of do that all, then we have to aggregate that side of it. So the reducer side of that basically implements that. So what this does is it basically takes the output from the map, and it says, okay, now I'm going to split and collate each given word, and I'm going to send it to the same reducer. And then that reducer is going to add up how many times it sees that one word. So it's kind of like a group by, and a partition group by, if you want to think about it in terms of database talk, right? So I split all my file into words, and then I send each word to a specific thing, kind of like a hash function, right? And they end up being counted, and then at the end, there's a final aggregation. So if you were going to do this in the raw MapReduce framework, which is a Java API layer, here's kind of how you would do it, right? So that was the pseudocode. Here's an actual implementation. I don't expect you to read this, but it basically is about 60 plus lines worth of code. Not too hard, but is a lot of code, right? So just wanted you to take a mental picture of how long that is and place that in the back of your mind for further discussion a little bit. So a picture tells 1,000 words. So here's a little example of word counting. So have on the left a file that has 3 lines and 3 words per line. And how this gets split up by the mapper is we basically do one line. We read one line, split up the lines, and distribute those lines among the mapper processes. And then each one of those mappers applies the map function. And as I mentioned, we take a word, split it, and emit the number 1. So under the mapping column, you can see that each line is split into one or more lines containing those values. And then there's what's called a shuffle phase. And that's just kind of aligning the keys so that all the keys are grouped. And then those keys are then sent to reducers, and the reducers then add them up. And finally, as output, we get an aggregation of each word and the number of times that word occurs. So kind of just basically, if you were going to do it in SQL, and you had a bunch of you basically split the input into words, and then select word count star group by word, right? So that's kind of really what we're doing as a simple example. Now, since most of you, I assume here, are somewhat SQL savvy. Anybody not SQL savvy here? Oh, cool, no hands. Okay, so for those of you who are SQL savvy, I present to you Hive. And Hive is a high-level language, very much like, that includes a high-level language called HiveQL, which is very much like SQL. And Facebook designed this because they found that it took a lot of time and effort to write raw MapReduce code, right? You saw the example how many lines of code there was, just to kind of perform a simple statement that most of you could, type faster on your phone than, anything else in SQL. So SQL has a lot of benefits. A lot of people know it. It allows easily to express fairly complex things in relatively small amounts of lines. So how it kind of works is that there's an interpreter. So Hive has an interpreter that takes the SQL-like code and then converts it into MapReduce code that then is submitted to a cluster and is run as a big MapReduce job. So this is the parallelization of kind of what happens. So this is how you can kind of run SQL on a Hadoop cluster in a massively parallel function, giving you massively parallel functionality, right? So probably, how many people know how much data, or I've heard how much data Facebook has, right? There's a lot of memos or blog posts that come up, but I think, definitely they process tens of terabytes of data per day, right? So that's probably a lot more than most people in the crowd process, or maybe even have in their whole company, but that's the kind of scale that Hive and Hadoop and MapReduce are running at Facebook, which solves some pretty big problems over there. So at the end, it kind of returns results to the client, much like a SQL-based process. So a little bit more on some Hive details. So Hive basically has a schema on read. So what does that really mean? That means that the data in HDFS that you copy there can be copied there outside of Hive knowing about it at first, right? So when you read the data, at that time, it basically parses it into columns and presents that data as a projection, right? So it's a little bit like an external table in Oracle, if you will, in much the same fashion. There's really no type checking ahead of time. It's all done at execution time, right? So think of it a little bit like an external table. And it basically supports the typical scalar types, float, double int, string, etc. But it also has some complex types, including a struct, map, and array. And I'll get into a little bit in some of those. Those basically allow for nested structures. And Hive has what we call a metastore. And the metastore basically contains the table definition, if you will. So in Hive, you declare a table, you create a table, and it's the metadata for that table, essentially the DDL, is stored in a metastore. And that's how we know how to kind of map the projection in Hive from the data that lives in HDFS. So a little bit of a comparison slide for you guys. I figure this is kind of useful. So HiveQL is quite similar to SQL, but it's basically a little bit like a SQL 92 dialect. It doesn't contain all the features in SQL 92, but also has a couple Hiveisms. So it doesn't have window functions currently and things like that. It's what I would refer to as what most people would probably understand as basic SQL, right? Select, group by, having, etc. As far as update capabilities, Hive is not a database. It's a database-like interface to data within HDFS. So it doesn't support insert, or only supports insert, not updates or deletes. So file data is basically immutable. You can't change it, right? Compared to a database, obviously you can modify data, update, delete it, etc. It also doesn't, Hive also doesn't really support transactions. So it's not an OLTP database. It's not made to do transactions. It's more of an analytics platform, right? So the data is already kind of created for us. It maybe is output from something, and we want to perform analytics on it. We don't really need to do transactions, you know. And a lot of times in most data warehouses, you don't need to do transactions either, right? You're just taking a bulk data set that you extracted from somewhere, and you're loading it in, and then you're going to run some analytics on it, right? So even though your database may support transactions, for the most part in data warehousing, you're not really using transactions unless you're doing something more sophisticated like change data capture, etc. Latency is also a bit different. So a lot of databases have, you know, sub-second response time for things, right? However, in the Hadoop land, it takes a little bit of time to spin up things on a 100 or 1,000 node cluster. So the kind of response time we're looking at is in the minutes, right? So this really, Hive is not probably a solution to run or real-time analytics right now, right? So that's not where it stands, but it can do quite meaningful aggregations on extremely large data sets. Also, index-wise, Hive supports indexes, but not in the way that you think of indexes in RDBMS. I won't go into a lot of detail in that, or much at all, but just kind of throwing it out there because it's a comparison point. And as far as database size go, Hive and Hadoop have been proven to show scalability into the petabyte range and Hive petabytes, and most RDBMSs are probably in the terabyte range. I mean, there aren't that many petabyte-sized relational database warehouses out there, and probably for a specific reason, right? I mean, how many people know of petabyte-sized relational databases out there, right? There's a couple, but you probably can count them on both hands. So one of the things I think most people who work with Oracle and data warehousing are familiar with is partitioning, right? It's kind of a core concept in VLDB. You know, the smartest I/O is the one that you never have to issue, right? So data elimination is a big part of that. And you can partition tables in Oracle and other relational databases. You can also partition data in Hive. And basically how we do that is we can create an external table. So when we create an external table in Hive, basically we're saying, much like an external table in Oracle, we already have a file on the file system that contains the data. And here's kind of what the projection of that data is going to look like. And we also specify some partitioning columns. Now, unlike Oracle, when you have multiple columns in the partition by clause, it's essentially a level. It's a hierarchy, right? So think of this as more like sub-partitioning. So in this case, it's 3 levels of partitioning. It's not a combination key per se, right? And part of that you can see at the bottom where I actually have the directory structure. So I have a directory structure that basically is year, month, and day, right? So I've basically sorted my data on my distributed file system and placed data that only meets that criteria out there and then associate it with a specific partition, right? So think of this as like ETL or ELT, right? So as you're doing data processing, you can filter your data, choose a specific restriction on it, and put that output into specific directories to later be consumed by Hive, right? So one of the kind of interesting things that's in HiveQL that's different from regular SQL is that HiveQL has what's called a sort by as well as a group by. Now, order by. Order by is what you would presume it would be. It's a global ordering of a result set. Now, in MapReduce, because we're on a distributed platform, that means all the data has to end up being seen more or less by one reducer, which is one process, right? And that's not really a great scalable way. And a lot of times you don't necessarily need to order everything from beginning to end, but maybe you would like clustering because the output from one query or one command is the input to something else, and maybe you're looking for better compression or locality, etc. So HiveQL has what's called a sort by. And what sort by does is a local sort. So each reducer that's doing work, each parallel thread sorts its own data of what it sees. So it doesn't do a global sort, it only sorts what it sees. So when the output is written, each reducer essentially writes one file, and that file is sorted within the file. So you can do maybe concatenation of things or stuff like that to do an order by, a full order by later. But a lot of times a full order by isn't needed. So this is kind of one interesting feature that's a little different that I thought was worth mentioning. So since I showed you the MapReduce word count example, I thought we would use the same example to show what a high-level language like HiveQL, how we can accomplish the same thing. So obviously, you can actually read this one, right? That's why I kind of told you to take a picture in your memory. It was like 60-some lines. Here, this probably looks pretty familiar to anyone who's familiar with SQL, I would say. So basically, what we do is we create a table that we call document, and it basically has one column, which is the entire line in the file. And in this case, we're actually going to load that data into a table called document, which is a Hive table. So this is one way that you actually can load data into a table. So in this case, it's not an external table. We're actually going to create a table within Hive. So after that, we actually do a CTAS, which kind of splits up the data. We take each line, break it up by space, and then there's a little function called explode, which essentially takes each one of those and returns it one per line, right? And then we do a group by and an order by, and that probably looks pretty familiar to anyone. So the point of this slide is that you can write a lot less code using a higher level language like HiveQL than MapReduce. And so you don't have to be a MapReduce programmer to use Hadoop. You can use a familiar tool that probably most of you are used to, HiveQL, which is similar to SQL.
Great. Does load data do the same thing, like sort of small regards to your loading?
Yeah. So load data is the question is what does load data do? And load data does basically fire off a job to load the data in, right? So MapReduce job will go and read these files, basically split it up and then write it into the Hive table. So I thought we'd have a little fun and push things in a direction that probably is a little bit more difficult to do with a relational database. And one of the guys that I work with at Cloudera did a little example on how to query tweets from Hive. So I'm sure everyone's familiar with Twitter. So how can we capture some data from Twitter? Twitter has an API and do some interesting things with it. So I'm not sure, probably many of you don't know, but the output from the API at Twitter comes in a format called JSON, right? So that's why I have my little laughable icon there. Hello, my name is Jason. And JSON looks like the format on the left. So it's kind of a key value based output, and it can be nested, have nested data types, right? So all the blue highlighted values are the name, and then on the right-hand side of the colon is essentially the value. And that probably looks fairly familiar to someone who's worked with XML. It's kind of similar. And a lot of web applications today use this format because data is very portable. It's self-defining. The schema is essentially included in this text, right? So I can give somebody a JSON structure, and I don't need to give them any external reference to that as to what it is. It's self-contained, right? So a lot of applications use this for portability. So just kind of a quick thing. In this example, we basically have Twitter as our cloud in the internet. And then we used one of the Hadoop Ecosystem tools called Flume, which is essentially a data pipeline tool. So you can take output from something that's emitting data, create a pipeline, and write it into HDFS and do things along the way with it. So it's kind of like a JMS, if you will, for those of you who are familiar with JMS. But this is a distributed JMS, more or less. And then in this case, we write it to HDFS. And then we kind of have on the right-hand side Hive, and we're going to query HDFS to kind of see what the data looks like. So hopefully most of you can read this. This is kind of like our external table, right? So I've highlighted a few things in color that are a little bit different from the standard kind of what I would refer to as flat data structures that a relational database has, because our JSON can be leveled, contain a hierarchy. So actually, we can define a table in Hive that matches that hierarchy. So you can have a structure, and that structure can contain an array, right? So it's contain, say, one or more strings. So like, how many people are familiar with hashtags and tweets, right? You can have more than one hashtag in a tweet. So you can see on the hashtag line, kind of, I guess my battery's dead, that's fine. There's an array, a structure of strings, right? So we can have one or more instances, or 0 or more instances of a hashtag, right? So we don't have to define a relational structure and split that off into a key and then the number of occurrences in that key in another table, right? We can kind of keep it all together in a nice little package and not have to do that. And then kind of at the bottom, we have our table partitioned by time. And there's a line there called row format SERDI. So what SERDI is a stands for serializer, deserializer. And what that is when data is written into HDFS, it basically gets serialized as some structure notation that's written as a binary format onto HDFS. And then later, because it's binary, we have to figure out how we're going to read it back. So we kind of have to have a way to do that. And we're telling it like this. So in the Oracle external table world, I would call this or kind of related to the preprocessor, right? So with external tables, you can have a preprocessor, right? So you can take data from a text file and maybe manipulate it in flight, and then you project out columns, and that's kind of what we're doing here. We're basically saying preprocess the data from HDFS using this guy, and then project it matching this table definition. So because we have nested data, we can then also write queries against nested data. And they're not terribly complex. In this case, basically, this is a simple query that queries some attributes from the tweets table, where the tweeter was myself, and the retweeter was Gwen Shapiro. I thought maybe she would come, and it would be funny, but I guess not. She'll have to watch the video. So that's kind of some cool things you can do with Hive, and I think for most SQL-related people, it should come fairly easy, and you can do some interesting things with that, and including nested data and stuff like that. So next, I would like to talk to you about another high-level language for data processing called Pig. Pig has a language called Pig Latin, and Pig was kind of created in almost around the same time as Hive was created. At Yahoo, Facebook was using Hive, and Yahoo was using Pig. And Pig also is an interpreter. It converts the Pig language into MapReduce jobs, right? So the kind of cool thing is that Pig actually is kind of like a data pipeline processor, but really it uses a directed acyclic graph, which is this kind of fancy term for a pipeline that can have more than one output. So like pipelines have one input and one output, and in this case it's a graph. So we don't necessarily have to follow the same restrictions that a true pipeline has. So it's a little bit detailed, but it's kind of cool. I'll get to why that's important later. So a couple things is Pig Latin is basically procedural. It's a kind of a top-down language, and it's unlike SQL, which is kind of an inside-out. So it's a little bit more like PL/SQL than SQL. And it has something that's kind of cool called lazy evaluation. So you can basically program a pipeline in the shell in Pig, and then just do describes and things, and kind of describe what most of you are probably familiar to as row sources, right? So you can say, if I join A and B, what does the output of A and B look like? You can do a describe on that. And I'll do a little example at the end that kind of shows that, which is kind of neat, because it lets you understand what the data looks like at any point in the pipeline. Also, data can be checkpointed. So a lot of times, Pig is used for big ETLs or ELTs, if you will. And along the way, the developer may want to checkpoint that pipeline. So if something fails, he doesn't have to go back to the beginning of that pipeline and restart. Now, the cool thing is doing that checkpoint, you just can continue on, and then if it does fail, you can go back to the point you checkpointed at. So, and for those of you who like to be in control, you can actually basically program your execution plan with Pig. Or you can rely on the optimizer to kind of choose it for you. And if you're very savvy with your data and understand how Pig works, then a lot of people will do it by hand because they can get a little better optimization, as is usually the case, than relying on something else. So it also is really cool that it supports splits. And this is why I said that the acyclic graph was important. So we can actually split a pipeline into two different things and continue in parallel processing from that pipeline. So how this kind of comes into play is, say you're rolling up some data and you want to do an aggregation on the data on, say, A, B, and C, but you also then want to do another aggregation at the same starting point on D, E, and F. You don't have to go back to beginning and get all the data. You can continue from that point on in parallel and have two streams then working on this that have the same data set source. So it's kind of cool like that, and one of the reasons that it's used for big ETL. Also, you can pretty much put any UDF in the pipeline. So going into some of the Pig data model types. So there's a little bit of difference here from the relational database side. So what the basic element is called an atom. So this is basically a scalar data type, right? Your int, long, string, etc. And kind of an example of that is just a basic string. And a tuple, for most of you who are database savvy, a tuple is just a sequence of atoms, right? And they can be of the same or mixed type. So by that, what I mean is if you think about a row, if you will, that can have multiple definitions of the row type in it, right? So this is where things kind of blur and deviate from strict relational database land. And then they refer to as a bag. And a bag is kind of a set of tuples. And kind of a bag is a little bit like a table, but it doesn't follow a strict format of a table. So it can be, the rows can be of different data types or different columns even, depending on if that's really what you want or not. And then there's a map, which is basically like an associative array. So for those of you who are kind of familiar with query compilation and Oracle database, here's kind of how the Pig interpreter works. So essentially, we take a query, and we parse it, and we, of course, do semantic checking. And that basically gives us a valid statement that we can run. And then that valid statement is fed to a logical optimizer. And that's translated then into a physical plan, right? So this is kind of like what we're going to do and then how we're going to do it. And then that physical plan is then translated into a MapReduce job. And then that MapReduce job is submitted to the cluster. So what's really cool about Pig, because this is submitted as a MapReduce job, is that if you have a Hadoop cluster, there's no such thing as a Pig server. You can have Pig installed locally on your laptop, write a set of code, and what it does is it submits from your laptop to the Hadoop cluster a MapReduce job, right? Which is kind of cool. So there's no server-side software. It's just all the translation kind of takes place in the Pig engine on the client side, right? So some of the relational operators that pig allows you is somewhat related to the SQL world. We basically have load and store. Load is to read a table, store is to write a table, or read input and write output. And then filter is kind of like your where clause, right? So you basically filter by something, and I have an example that I'll go into. Join, obviously, same as SQL, meaning there. Cross is for cross join. Group and co-group. Now, co-group is something unique to pig. I won't go into the details of it, but it basically allows you to do grouping without having an aggregation, right? So most group bys want you to have an aggregation. Co-group kind of lets you sidestep that a little bit, but what it does is it creates more like the output of list ag instead of a group by, right? So it kind of creates a horizontal aggregation or listing versus a vertical listing. So that's a lot to go into, and I know this is kind of most. I'll just kind of brush over that for you. And then for each generate is kind of like how we can do groupings and emit. Order by distinct, union split, limit, those should all be fairly self-explanatory. Okay, so examples. We're going to fall back to our word count, and I guess the red's a little hard to read, but I'll go through it. So basically, we have, to read in our file, so we're going to load a text file, and there's a thing called a text loader, which basically just reads in the data as one line, and we're going to place that into a column, more or less, that we call sentence. So that's kind of the projection. And then we need to calculate our words. So here's an example of for each generate. So for each of the lines that are in our file, we're going to do something. So it's kind of like a little bit like a for loop or nested loops. And we're going to basically take that sentence, that list of words, tokenize it, which is basically splitting it up into individual words. We're taking the sentence and breaking it apart. And then we're going to flatten it. Because in pig, when you do something like this, it basically makes a horizontal listing, not a vertical listing. So we're going to flatten and basically pivot. So we're going to take our list of words that are currently horizontal, and we're going to pivot it so now it's vertical, kind of like rows, right? And that's what we're going to get in the words. And then we have to perform our group by, right? So we're going to group the words output by the individual word, and now we have that. So we basically have a list of horizontally words, how many we have. And then for each of those, we want to generate a group and a count star. So we're counting the word and the number of times the word shows up. And that's how we do that. And then store is basically write this output into a text file. And we're using what's called pig storage, which is just a method that basically outputs tab delimited records into a text file, right? So that's kind of a little bit of what pig is and how to use it. Example, probably the most prominent use case with pig is ETL pipelines. A lot of places use this to process extremely large amounts of data, and it's fairly easy compared to raw MapReduce code to write, as you can see. And it's a little bit more programmatic. One of the nice things about pig is that when you're writing large data pipelines and you're using a lot of grouping functions, like in SQL, you end up kind of writing this inside out, right? So a lot of people have moved off of doing external-based ETL, and now they more or less load the raw data into their database and use the power of a parallel database to kind of churn through their data inside and then write it. So it's kind of more like ELT versus ETL, right? What pig does is you can kind of do that in processing in pig, right? And instead of coming inside out, you can basically do top down. So sometimes I know I've written or converted ETL code, and I have 4, 5, 6, 7 different deep aggregations, right? Because especially if you're using things like window functions, right? You can't perform any operations on the output of a window function. You actually have to nest it, right? So if you want to do top n lists, right, and filters on top n, you say I want to calculate each top n, but then in order to figure out, say top 5, I have to wrap that in another SQL statement and then put a, where window function equals or a range of values, right? So you're thinking inside out. And you can do this with common table expressions, but sometimes with longer SQL statements, your definition of that is up here, and the implementation of it is down here, which makes it a little hard for humans to kind of put together, right? So Pig kind of allows you to basically write code as you would an optimizer plan, right? So you're kind of really writing at that level, but it's in fairly simple terms, right? So I have a little bit of demo that I thought was kind of cool just to kind of show off Pig. So hopefully I'm not doomed to crash as most demos are. All right. All right. So first, I'm going to just show you a little bit of SQL. And how many people aren't here? Oops. I guess I have to do mirroring. And I don't know where my screen is. All right. That's not going to work. Sorry for the technical difficulties. One moment, please. Okay, there we go. Okay, so here's just kind of a little output that probably most of you are familiar with. This is actually from the Scott schema that you may or may not have heard of. And this is our infamous emp and dep tables. All right, so I just have a basic SQL statement here. That's a two-table join with some predication and an order by, right? And in front of me, I have the output. It scrolls off to the side, but we don't really worry about that. So what I wanted to show you is how to implement this in Pig, right? So we take a really basic example, kind of show you the word count, but from a SQL perspective, thought it would be useful to take a SQL statement and convert it into Pig. So how that kind of looks is like this. So basically, we first load the emp table and the dep table, right? So we basically have a CSV file that I created of each one of those tables, and I'm reading it in. And on here, you can see I'm actually defining the table. That isn't necessarily, you can do or use Pig without it being a schema definition, but I'm choosing to do so. Then, like our SQL statement, we have to filter out our accounting and research. So basically, I have a line here that says, okay, I'm going to take the input from dep. I'm going to filter it where the dname is accounting or research. I'm going to take those results and put it in dep filter. Now, that kind of does our filter, right? So I think someone wise once said, filter early. So that's kind of what we're doing here, right? We want to filter early to reduce our result set, not do it later. In this case, we're going to do our join. So here we basically are joining the ep and dep table, or more correctly, the filtered dep table to the emp table here. And you can see that we're using joining on depno from emp and depno from dep filter. Now, we have to generate the columns. And so the projection there, we're going to take the emp and dep join, and we're going to emit columns. So you notice that here we have all the columns from emp here, but only 2 columns of the 3 from dep. So I actually have to choose one of the columns and erase it. Otherwise, we're going to have 2 depno columns, which is the missing projection from dep. So here, basically, on the emp table, you can see that I'm selecting emp. This is basically starting with the emp no column, to the depno column. So it's kind of like a way to select a range of predicates, or range of projections. So if I wanted the first 3 columns, I could do first column, dot, dot, third column. Just saves on typing. And then here, I basically am choosing the 2 columns from the dep filter. And then the result here is we're applying an order by from the projection, and we're going to order by emp now, right? So as you can see, here's kind of our 8 rows of output. So what I'm going to do is load this up into Pig. So basically, pig-x local is a way that you can run Pig on your machine without submitting it to Hadoop cluster. So you can actually run all of this on a local data set, all on your laptop, which is kind of cool. And you don't only need to download the pig source code. It's just Java. It's just a directory, right? So there's no installation. It's just unpack a directory and go. So what I'm going to do then is bring you into grunt. So grunt is just kind of like your SQL plus prompt, right? Kind of funny name. Probably makes me giggle, but. So then what I'm going to do is I'm actually going to select all of this and paste it into here. So as you can see, we haven't really done anything yet. We just typed some stuff in. Now, remember one of the slides I showed you said that pig does lazy evaluation. So it doesn't actually execute anything until you either use a store command or a dump command, right? Which we have not run yet. So we can also do something really cool, which is actually describe things. So let's actually describe what the output from the join looks like, right? So you can actually see here from the emp projection, we have the column names and the data types, right? So we can, that's kind of cool, right? I mean, this is something that you can't really do in SQL right now, right? Because SQL is kind of like parsing it, and then that would be letting you then see the output at different points in the execution tree, right? So this actually shows you all of it before it's even executed, right? It basically is only parsed it, and we can go in and describe anything. To see what the shape of your data looks like if you're using more complex types, which is kind of cool. So then basically what we do is we can see what our output looks like, and we're going to actually dump the result, which dump basically means give it back to standard out, or you can use store to actually write it to a file. So now you can see this is actually running some simulated Hadoop code, because I don't have a Hadoop install on my laptop. I only have this set of files that I downloaded, which is the pig source, or the pig code, right? I also might mention that the response time isn't instantaneous. You know, it's actually going through now and doing all that compilation and the plan, and then giving me the output. So here we basically have our output. So it's kind of looks like this, right? So this is our output, and if we kind of go back here, I kind of cheated and pasted it in. You can see that basically the output from pig matches the output from our SQL query, right? So I thought it would be useful, since it's probably new technology, just kind of how to navigate a little through it and what you can do. So here's this basic example of how you can interact with pig. And like I said, the only installation to run pig on your laptop is to download the file, unpack it, and run it. No, there's no other software that's needed other than Java. All right. So just kind of in review, some differences between Hive and pig. So Hive language is HiveQL. Pig language is Pig Latin. The schema for Hive is defined in our metastore, so we do have to define a schema up front. Pig, we can define it on the command line. Like when I showed you my examples, I said what the data types were, but there's no other store that outside that command line that has that metadata. So it's kind of done in the program or in your script at runtime, optionally. With Hive, it's not a server, like a relational database server, but it does have a JDBC or ODBC API. So you can actually use tools like MicroStrategy or Tableau, et cetera, that support HiveQL and run queries on Hadoop cluster and get the results back into those tools. Pig only has basically a Java API, which is one of the reasons that Pig is generally used more for ETL processing pipelines and not generally a query tool for users. So at this point, I think we're kind of right on time, maybe a little over, so I'll select questions from audience. Mark.
You mentioned about queuing to a single process with the order by, but if you did the local sort on each of the components, can it do a tree, graph tree?
So the question is with the sort by versus the order by in Hive, can the output be concatenated? And that would only be true if the input was ordered, right? right? So we're not actually ordering it. It's like a hash function output.
That's not what I asked. I asked if you local each component, can it not also then have a group by that then does the tree structure to gather locals?
I don't think that's supported today. That's a little bit more complex. But like I said, generally, on very large data sets, like order by isn't necessarily needed. Because if you're going to, order by is probably useful for a set of data that you're going to look at, right? A human will read. So ordering on extremely large data sets probably isn't a problem that is at the top list to be solved.
And the other quick question is from the graphic. Is Hadoop Skynet?
Is Hadoop Skynet? No, Hadoop is not Skynet, but it may take over the world someday. Yes?
Greg, I don't know quite what Cloudera is, but where does Hadoop fit into your company? Why are you guys using it internally for your customers?
So Cloudera, the company, has a package and distribution of Hadoop. So all the components of Hadoop are open source. So the Apache group has a site that all the source code is contained on. And many people from many other companies work on the source code. And part of the challenge with the Hadoop environment is that a lot of the projects are worked on independently. So there are different revisions of each of those products. And what Cloudera does is basically choose a release level from each one of those and creates a distribution that works together, right? So you don't have to figure out the dependencies between each project. You can just get the distribution, and we've done the work for you in that sense, right? Any other questions? Yeah. So the question is, for store in Pig, you can write it to a file. That file can be in different formats. So it can be text, and there are several other data formats within HDFS that I didn't go into because those are some pretty low-level details. There's things like Avro, RC files, sequence files, things like this that are basically serialization and order, different, more binary types rather than plain text. Right. Yeah, absolutely. Yeah. So. Yes. Yeah. By default, store will write it back to Hadoop. So if your data is in Hadoop, it will write it to Hadoop. Now you can store it locally, so you can get a output stored locally, or once you write it to Hadoop, you can actually copy it out locally. Those are both options. So that's a good use case. So if you're doing an ETL pipeline, right, and you're bringing in all your data into Hadoop, and then you run a Pig pipeline on it and get your ETL done, and now you want to say, put that in a relational database, right? You can get text output that you can easily parse and load into any relational database, right? Yeah, I mean, it's an HDFS. So any of the components that are in the Hadoop stack, more or less have interfaces to the data, different data storage types. Right? So any other questions? Yeah. Is there a concept of indexes? Not really. The Hive indexes are a bit different, and most of the reason behind that is that when you're doing processing with like Pig or Hive, your data isn't really in a format to be indexed, right? You can build an index outside of it to help you if that's part of the programmatic thing, but we're not going after a small number of records, right? I mean, essentially, this is a full table scan, right? So we're just plowing through our data massively in parallel and invoking it on hundreds or thousands of machines to kind of churn through it, right? So it's more of a batch process, and indexes really are becoming less and less useful in that sense because of the streaming capabilities and the parallelization techniques that are out there today. Right? So, yes. So the question is that Pig doesn't have any server, and Hive does or doesn't. So technically, neither Hive nor Pig have itself have a server. There is a project called Hive Server that is outside the interpreter itself. The main difference is just the API. So the client can get results returned via a ODBC or JDBC API with Hive, but Pig not. But it's still not a database server. So it's not like a session. It's kind of like submitting a job and having that process, hang on to that and just return your results, right? So there's not a server component to Hive interpreter outside of a different project called Hive Server. Yeah, so both of these are kind of like translation layers. So they take higher level languages, translate them into MapReduce jobs, which are then submitted to the cluster. So I think we're probably good on time. So I definitely want to thank everyone for coming. Hopefully that was interesting, useful, and informative.